So in our previous videos, we have already talked about different types of relations, symmetric, antisymmetric, in fact, reflexive, transitive, and all of them. In this video, I'm going to talk about another special type of relation known as the equivalence relation. So let's get started. As usual, I'm going to start with a very simple example. So we have taken a set capital L of all possible lines in a plane. So what I'm going to do is we define a relation on that particular set given by the basic relation of is parallel to. So basically a line is related to another if the first one is parallel to the next one. Okay. Now if you think about some special properties that we have seen in a relation, you will notice that you take any line L1, it's parallel to itself. So any line is related to itself. So this is reflexive. Now I'm taking another line L1, which is actually related to L2. So basically L1 is parallel to L2. Now if you actually explore the properties of parallel lines, you will see that L2 is also related to L1. So this is symmetric. Similarly, suppose L1 is related to L2 and L2 is related to L3. So basically L1 is parallel to L2 and L2 is parallel to L3. Again, from the properties of parallel lines, you will understand that the property is creating transition from L1 to L2, L3 via L2. So this is transitive as well. Now, if you look at this relation, it has all these three properties of being reflexive, symmetric, and transitive. So these kind of relations are together called an equivalence relation. So mathematically, what you need to do is, for an equivalence relation, check whether it's reflexive, symmetric, and transitive or not. So they have to hold simultaneously. For reflexive, you'll start with that. You see whether all the possible pairs of the form small a comma small a is there for all a belonging to the capital A. For symmetric, you need to check whether for a comma b, we have b comma a present in R or not, and this has to occur for all possible AB in capital A. And for transitivity, we have AB and BC in R together implying AC in R. So these are the things we have already talked about individually. So for an equivalence relation, you need to check all of them. Even if one fails to be there, it won't be an equivalence relation. Otherwise, if all of them hold simultaneously, we are good to go. So let's see a very simple example here. So these are the things we need to check. So this is A and there's a relation R on A. So I'm starting with the most basic reflexive thing, which is very easy to check. So you see whether 1, 1, 2, 2 and 3, 3, all of them are there or not. The answer is yes. So this is definitely reflexive. Now for symmetry, we don't need to check the diagonal elements. So I'm just checking the things which are of the form A comma B, where A and B are not equal. So for 1 comma 3, I have 3 comma 1. So we are good to go. This is symmetric. Now for the last one, transitivity, I'm starting with each and every element and check whether there's any other element which is beginning with its second component or not. So for 1, 1, 1, 3, we have 1 comma 3. Next for 1, 3, 3, 1, we have 1 comma 1. For 1, 3, 3, 3, we have 1 comma 3 again. For 2, 2, we don't have such elements starting with 2, so we don't check anything. For 3, 1, 1, 1, we have 3, 1. For 3, 1, 1, 3, we have 3 comma 3. And finally, we have 3, 3, 3, 1 for 3 comma 1. So we have checked all the possible pairs of the type AB and BC and seen that A comma C is there in R. So obviously, this is a transitive relation. So we see all the properties coming together. So this is clearly an equivalence relation. So this is something you need to understand. For each and every equivalence relation, we check all these things. Now that you have already seen an example in the roster form, I'm going to go ahead and show you an example in the separator form. I have taken a relation capital R based on the basic set of all real numbers given by x is related to y if and only if x minus y is an integer. So belongs to z means belongs to the set of all integers. So we are going to check the properties one by one. I'm starting with reflexivity. So for reflexivity, what do? You take any element from the original set, which is the set of all real numbers here, you see the same element and check whether they're related or not. Now, what is the definition of the relation here? You check their difference. The difference comes out as 0, which is definitely an integer. So this is reflexive. Next, we are going to check whether it's symmetric or not. For symmetric, again, you know the general rule here. I'm going to start with the pair A comma B. So for A comma B, what is the basic definition of the relation? A minus B is an integer. Now you know that A minus B is an integer implies that B minus A is also an integer, because that is nothing but the additive inverse of that. So we can definitely say that B minus A is also an integer. Just think about this. Suppose the difference is 5. So if 5 is an integer, then minus 5 is also an integer. Now, if you look at the definition again, you will see that B comma A is a part of R. So this is what we look forward to whenever we are checking symmetry. So this is perfectly okay. The next one, which is the last one, is transitivity. So for transitivity, I'm going to start with two pairs here. The first one is A comma B and the second one is B comma C. Always check whether the second component of the first pair and the first component of the second pair, whether they're equal or not. So now I'm going to use the definition of the relation. So A minus B is an integer, B minus C is an integer. So this is the definition. Now we are going to manipulate it. Now if you add two integers, that is also going to be an integer. So I'm adding A minus B and B minus C. So this B is getting cancelled and you're left with the fact that A minus C is an integer. Now when you think about the definition of the relation, it's very obvious that A comma C is actually in R. So this is what you observe for A, B, B, C. You have AC. So obviously this is transitive. So if you look at the relation now, all these properties are satisfied. So this is an equivalence relation. So I hope you understand what these things are, and this is very crucial because for this particular type of relation, you need to check all the properties together. So it's a good practice for you. So go ahead. I hope you understand the basic definition and how to check this equivalence relation or not. So practice. In the next video, I'm going to talk about a special type of relation known as the identity relation. So stay tuned.